an ordinary kitchen blender, an old-fashioned power drill, a demolition hammer. As different as these objects may appear from the outside, they have one thing in common. They are powered by a universal motor with triac-based motor speed control. Phase angle control circuits and the thyristors and triacs they are based on have been with us for decades. However, when combining them with modern microcontroller technology, we can obtain control over powerful mains-powered loads, like motors, lamps, heaters, and many more. In order to show you how that is done in a rather inexpensive way, we will proceed as follows. We will take apart another home appliance that relies on a triac, a bread baking machine. I will tear it down. We will then have a look at the electronic controls and connect them to an Arduino Uno. Experiment with that setup and hopefully learn how it all works on the circuit level. A bread maker like this can be purchased as a used item on eBay, often for just a few euros, dollars or pounds respectively. To find out what a used item is really worth, go on eBay and look for sold listings to see what people have actually paid for any given item in recent weeks. Here are some examples from the German and American eBay pages. One of these home bread makers usually has two directly mains-powered loads, a heater and a motor, usually being switched on and off by a relay and a triac. Disclaimer. In the following minutes I'm going to experiment on mains-powered circuitry that has no electric isolation from the grid. Even some of the solder pads and components on the control part of the circuit are live and thus very dangerous. Later in the video, protective measures such as isolation transformers and optocouplers are discussed. Don't work on these boards without those protective measures. So here we are again with our electrical setup, and in the meantime I have made a few minor modifications to the layout of these wires here. Now the overall circuit diagram is still the same, the electrical connections are identical. I simply tried to shorten some of the wires and then screw them together with these screw clamps here to make it look a little more tidy and make it easier to understand. The only thing that I changed electrically is to replace the heater with this light bulb here. And the purpose of that is that we have a visual indication when the relay is turned on. Because if I had the heater, then I, filming this, would be able to feel that heat, but you out there couldn't see that in the footage. So that's why we replaced the heater with the light bulb. And what we're doing now is to choose between these different programs here that are listed here, going from number 1 to number 11. And this is stuff like normal bread, or in this case, for example, butter. And we're going to choose 7, which means baking only, nur backen, it's German for baking only. And that should mean that the heater is going on, but not the motor. So let's try to choose number 7. Pressing start, and the lamp goes on. And I can cancel that again by pushing stop. And number 10 is butter, and butter should mean heater off but motor on, because when making butter you would have the little hook in there turn. So again we're selecting a number, this time number 10, starting, and that turns on the motor, and I can again cancel that by pressing stop. So I think you get the idea. We can select different programs, and then the little chip on there will basically control these mains powered loads here, demonstrating that we have everything we need to control these relatively large electrical loads. And in case you're not that impressed by this little motor, let me just connect something else here for you to show that a larger motor could also be used with this circuit. So what I have here is a pretty big motor powering this fan here from an AC unit. I repaired this in one of my recent repairathon videos, and I have connected that to the circuit, and we're now trying to do the exact same thing as before, only with the bigger motor connected. And start. And we can also stop that again. And I guess we can turn it on once again. So, I think you get the idea. So here are the two circuit boards of this device. The lower board is the control board. It holds buttons, LEDs, 7-segment displays, and most importantly, on its bottom side, the chip that controls everything. Unfortunately, that chip was specifically designed for this particular job, and I cannot reprogram it. And that's why I'm removing the control board to make space for the Arduino Uno. So I have now connected this board to this isolation transformer here, and I did that for safety reasons, which I will explain in more detail in just a few minutes. And let me also show you why I connected these wires here to the board. Now the red one is connected to the output of that 5-volt voltage regulator, and the black one is the common ground of that circuit board, while these two remaining gray wires here are the inputs of the driver circuits for the relay and the triac. And I also connected these little extensions here to those wires to be able to make better contact. And what I'm doing now is to pull one of the gray lines down to ground. And as you can see, by doing that I can control the motor. And when I change this to the other gray wire, connecting that to ground, I can control the relay and thus the little lamp. And what I'm doing here by hand, pulling these inputs down the ground, can also be done with a microcontroller. And that's why we're now going to connect the Arduino board to this circuit. The connections I made are as follows. The board from the brad maker supplies the Arduino with plus 5 volts DC. And the Arduino, on the other hand, uses 2 of its I/O pins to pull the inputs of the drivers to ground in certain intervals. The program is very simple and is just meant to demonstrate that the Arduino can control the board. The source code of these example programs, as well as detailed circuit diagrams, will be discussed in this video after I have demonstrated what we can do with this setup. And as you can see, the lamp and motor are switched on and off in regular intervals. The Morse code sound comes from the little buzzer which I also connected to the board just for fun. In the next step, I disconnect the lamp from the relay and connect it to the triac, which until now was used to switch the motor. I'm doing this to demonstrate that the triac is much more versatile in its applications than an electromechanical relay. In order to extend the capabilities of this board, I'm adding a second full bridge rectifier and a trim part to the secondary side of the circuit's mains transformer and connect the output of that circuit to one of the analog inputs of the Arduino board. And of course, the program needs to be changed. As you can see, I have programmed the triac to slowly fade the lamp from minimal brightness to full brightness, then switch off and start again with the fade in. The fading is just there to demonstrate that the triac can be used as a dimmer. The bulb could also be set permanently to any of the intermediate brightness levels that we are sweeping through right here, if that were desired. This is an example for phase angle control. This approach is not limited to incandescent light bulbs though. It can also be used to control electric motors, and this just works best with universal motors. The original motor of the brad maker is an induction motor with motor capacitor, which is not the first choice when it comes to variable speed control. As an example for a universal motor though, I'm now connecting this German-made Fine brand power drill from the 1970s. I repaired this in my power tool repair marathon video that I made a number of years ago, which by the way has now more than 1 million views. In addition, a potentiometer is connected to another analog input of the Arduino and the board is again reprogrammed. And now I can control the motor speed of this old power drill by adjusting the potentiometer. But of course, as we all know, when it comes to using actual power tools, a standard potentiometer like this would not be that practical. It would be better if we could control it with a button built into the handle. And actually we can make our circuit here do that as well. Now, older machines like the fine drill often just have an on-off switch in the handle. In order to implement an upgrade, you can buy this part here for under €1 from the German website Polin, though. It's basically an unfinished speed control that consists of a plastic mechanism turning a trim part inside its enclosure. The actual power electronics part is missing, but that's just fine for us here. I can remove the standard part and connect this part instead. Now I know what some of the viewers, especially maybe some of the older ones, will say. Well, congratulations, you accomplished to build an overly complicated microcontroller circuit, achieving the same that others have achieved with a handful of parts decades ago. And to that I can only say, you're both right and wrong at the same time. So please hear me out. Here's a collection of circuit diagrams from classic phase angle control circuits, or Phasenanschnittssteuerung, phase cut control, as they are called in German. The first one is an example circuit from Wikipedia. The second one, a real-life dimmer circuit that I reverse engineered. The third one is a motor speed controller from a book from the 1980s. And the fourth one is another one that I reverse engineered, this time from a kitchen blender. I'm actually experimenting with these circuits here as well and want to cover them in another video. But while they are very good at their specific job, you gotta realize that the microcontroller based approach is much more versatile, and that with only minor changes the same circuit could allow you to dim a light, limit the speed of a motor, regulate the motor speed under load, control a motor in an automated process and run it in loops, attach sensors, or even give it Wi-Fi capabilities, and so on and so forth. Wisdom is maybe not to say that in earlier times everything was better than now and stick to it, but to judge fairly what actually was better and combine that with the best modern times have to offer. Call it the best of both worlds approach, and that's what I'm all for. But enough of the ranting. Let's analyze the circuit we found in the bread maker, explain the changes I made, and complement that with some source code examples to better understand what I actually did there. And maybe then we can see how we can improve the safety of the entire setup. Let's draw a circuit diagram then, and we're going to start with some of the external components, and that would be that motor plus capacitor, the heater that would normally heat up the dough, and I drew this here just as a resistor because at the end of the day that's really what it is, a very high powered resistor. Another external component is the mains transformer. It is very small to be true, but it is the mains transformer that delivers the supply voltage for this board. And speaking of which, that supply voltage is rectified, of course. And some of you might recognize right away that this is a full bridge rectifier. And then we have these two little components here that at first sight might look like resistors. They even have color coding on them, but as you can see there it says L there, so that shows us that these are actually inductors. And you will see a bunch of tiny capacitors on here, and the purpose of these inductors as well as these capacitors here is basically just filtering so that you get like a cleaner DC voltage. And next to the full bridge rectifier here we also have a couple of more diodes, but we will actually leave these out here because they are not really important for what we are doing here now. The board is supplying a couple of voltages other than the one that I'm going to draw in the circuit diagram but we don't need these in order to understand how the basic circuitry works. The same is true for the buzzer and everything surrounding the buzzer, because that's not what I want to focus on here. Following that full bridge rectifier, we have a relatively large electrolytic capacitor and then a 5-volt voltage regulator, and this is basically supplying the supply voltage, in this case for the Arduino. As I said before, in the normal configuration, the motor is switched by the triac, that's this component right here, and there is also a capacitor and a resistor next to it, and those are part of a snubber. This is basically to protect the triac. The heater is switched by an electromagnetic relay, and that relay also has this little protection diode right here, and that's because of the flyback, because of the energy that is stored in the inductance of the relay. But you cannot use the original chip or our Arduino here really to drive these components directly. What you also need is a driver circuit, and it's a really basic one, but it's based on these transistors right here, and these are PNP type bipolar junction transistors. And part of that driver are also a bunch of resistors and a little capacitor, but at the pins that we have labeled 1 and 2 here, that's where the signal from the Arduino I/O pin will actually come from, and where that microcontroller is connected to the original circuitry. So now that we have drawn the circuit diagram, it is obvious why the setup is pretty dangerous. Now you can see here that the triac is not only connected to the mains directly, but also to the common ground of the control circuitry. And in more practical terms, that means that one of the pins on the power cord here is directly connected to the ground, and thus the shield here, for example, of the Arduino. So first of all, if you were to build something like this and try to program it, always plug out the power cord before plugging this USB cable here into the Arduino. Because otherwise you would connect, if by any chance this pin here, for example, would be a line, so it would be hot, then the ground of your laptop would also be hot. So don't do that. Now, there are a couple of angles of attack here to make this circuit safer though, and what I did in the experimental setup was to insert the isolation transformer. The reason I did that was to separate the circuit here from the ground referenced power grid. Now, if you're not sure what I'm talking about there, then you should watch my 2 videos about that subject, about isolation transformers, earthing and so on, and you can find the links to that in the video description under this video. Another angle of attack, which is more practical for an everyday application, is to insert optocouplers into a circuit like that. And the purpose of the optocouplers is to separate the ground of the triac circuit from the ground of the control circuit. And 2 ways to do that is having an optocoupler, but then also a separate power supply for the Arduino. And the other option is to just insert an opto-triac into the triac driver circuit, and then you could even power the Arduino from the little transformer, but you would have to separate the triac from the ground of that circuit then. I have shown you examples of what the circuit can do. We have drawn a circuit diagram and I have proposed certain safety measures. Now let us go through the modifications I made in the beginning and look at some of the source code. The next thing I did after inserting the isolation transformer was to connect the Arduino's I/O pins number 9, 10 and 11 to the input of the triac driver, relay driver and buzzer driver circuits. The PNP transistor drivers invert the input signal, and that means that pulling the input to ground will activate these electrical loads. In other words, all that was necessary for the first test program was to do the following. First, the setup. The 3 pins 9, 10 and 11 are declared as outputs. And then follows a super simple program that is just an infinite loop starting by pulling pin 11 low, wait 500 milliseconds, then turn it high again, wait 500 milliseconds, pulling pin 10 low, wait 500 milliseconds, then turn it high again. Wait 500 milliseconds. This simply activates lamp and motor for half a second each. And then I try to mimic an SOS signal by rapidly turning pin 9 down for 50 and 100 milliseconds bursts. The program repeats then in an infinite loop. As you can see, this is a very simple program, and I always keep the source code I show in these videos as primitive as possible. This is all about concepts, not finished solutions. By switching a load like that light bulb on and off much quicker, it can be dimmed. The bulb is actually flickering, but the human eye doesn't really notice. Phase angle controls mean that you wait for the zero crossing point of the alternating voltage, then have a time delay and only switch on the triac later during that cycle. That way the light bulb only lights up for a fraction of each cycle. In other words, you can reduce the RMS value of the voltage across the light bulb over time, and that is accomplished at firing the triac at another point in time during each cycle, and that point can also be expressed as a phase angle, thus phase angle control. In order for the Arduino to know when the zero crossing in the mains voltage occurs, I added a second bridge rectifier to the transformer's secondary. A trim pot was added to act as a voltage divider to limit the peak output voltage to the 5-volt limit of the Arduino's analog to digital converter. That trim pot was then connected to analog input A0. And the fade-in program works like this. First, two variables that I called val and microsec are defined. Then pin 10 is declared as an output. Now a for loop starts. What this loop does is to count down from 9800 to 2000 in steps of 1. Within each step, the Arduino checks the voltage present at the analog input A0, and when that value has dropped under 5, which should represent roughly 30 millivolts, the input pin of the triac drive is pulled high, meaning the triac is deactivated. Now the Arduino counts to a number between 2000 and 9800 microseconds, depending on where we are in the for loop. Then pulls the pin 10 down, firing the triac and lighting up the light bulb. The lower the value of microsec, the earlier the triac is fired. The brighter the lamp will appear. The time and voltage values are empirical values, with which the circuit delivered the best results while filming. Again, I'm sure there are much better ways of implementing something like this in code. I just wanted to show that the lamp can essentially be dimmed to at least a few thousand brightness levels with this simple circuit. In the next step, I removed the light bulb and connected the power drill instead. And then I also added a potentiometer to the Arduino and was able to control its speed. The source code here was the following. It is quite similar to the last program, but this time we have no for loop counting down. But we still read out the voltage value from A0 to determine the zero crossing point. In addition though, we also read the value from A1, which is analogous to the output voltage of the potentiometer. And we multiply that value with a factor and use that as our time delay. So in other words, the higher the voltage on the tap of the potentiometer, the higher the delay, the slower the motor will run. Okay, so that was all I wanted to show you for today. The next Scrapyard Repairathon, episode 19, is already in the making and I will be publishing that soon. But I still wanted to know if you are also interested in little ideas and tutorials like this video here. If that is so, then please give it a like and let me know that there is demand. I can only speak for myself, but my ideal for this channel is a good mixture of repair videos, little inventions and tutorials, and I want to keep it that way. If you want to help with any of these undertakings, then please consider becoming a Patreon supporter on patreon.com/tpai or make a donation. Links for that are in the video description below. See you soon.